All right. Here's we have one more linearization to do. I believe at the start of the lectures at one point I said we deal with non-linearities. We had a couple to deal with. Well, the first one was valves. The second one is pumps. All right. So pumps are nonlinear devices. They would have pump curves associated with them. I'm not going to get a lot into that. When you go to take your fluids courses, they're going to get into this sort of thing and talk a lot more about it. So we're just going to look at how you would put a model around it. So here's what you have. So we have a pump that takes something out of atmosphere at atmospheric pressure and steps up the pressure. All right. And so that will create, because there's lower pressures down the line, that will incentivize a flow, of course. So here we have atmospheric pressure, we step up the pressure, and now we have a flow coming into a tank. Uh, so this tank has a capacitance C, pressure, we're calling it P1. There's atmospheric, it's an open top tank. And so you have a flow coming out here, but the flow out is regulated by this valve, which has a valve constant K. And then it comes out the valve and goes into another pond. So this could be like something used, uh, I don't know. You're pumping out of one place. This is basically a surge tank, and you're pumping it to the next for whatever reason. All right. So this is what the valve curve looks like. Wrong words came out. Excuse me. The pump curve. So we have it'll be some. Whereas before we had a curve look something like set yay. Now it's going like this. Okay. So so here's the pump characteristic. So we're operating at this nominal flow with this nominal pressure across it, and then there'll be and we're looking. So we're going to linearize, but the slope is now down, so it's going to have a slope minus q. Okay, and so once again we're setting these things up. Okay, so again, from our perspective, q will be given. This will be the slope in the curve, so you'll know that. And we could have all the same discussions about linearity and or about nominal and perturbation variables. Excuse me. So what do we do here? Okay, when you're looking at the flow here, I'm going to skip this line. Let's just go right into here. We have our nominal flow plus or minus, sorry, I didn't read right. There's a stray mark that was deceiving me. So the nominal flow, and then we have minus 1 over q, that's the slope, then times the change in pressure would give the, so if we had an increase in pressure, we would then, look what would happen, we'd actually come back here. If we have a drop in pressure, we wind up over there. So the negative works. And so we're kind of doing this just like we did with the valves. Delta P divided by 1 over R, except the R had a positive slope, this is a negative. So we'll call it Q, all right? So linearizing here, driven by the change in pressure, okay, times minus 1 over Q, because we're not going from X to Y, we're going from Y to X, all right? That's why that flips. And so I'll let you take time with the video later, take a clean shot of this and study that curve and understand what's happening here. So change in pressure, perturbation pressure times minus 1 over q. We will move along this line, and that will give us our, I should put here, no, this is okay. If I bring, this would give us our new absolute flow, but if I bring omega, the nominal input flow on, or the nominal flow over onto this side, then we would have the perturbation variable. Started to confuse myself, and it's easy to do on these problems. So here we are. The incremental flow is equal to minus 1 over q times the incremental pressure. And it's, I say incremental, it could go up, it could go down. This could go up, it could go down. So here we are. Now we'll notice the change in pressure. So we're going from up to here. The bottom of pressure is P1. So, and P1 hat is just going to be this, if we take off PA, we take off our P1, excuse me. If we take off the nominal pressure for P1, we're going to have the incremental P1, and that will equal the incremental delta P across here. Same type thing we saw last time. So we can linearize these things. Once we know what we're looking for, we're given these constants, we can write equations for our incremental variables or perturbation variables, whichever you want to call them, right here. Okay, having said that, we have a tank. We're looking at the derivative of the perturbation variable. I'll try to use that term. Derivative equals the flow in, perturbation flow in, minus the perturbation flow out. All right, so the perturbation flow in is driven by the pump curve, minus 1 over cube P1. So that'll be the incremental pressure down here. You're going from atmosphere to incremental P1. All right, and then we subtract off what the pump is doing, and again, that's incremental P1. Flow out, that's why that negative 1 over R P1. Now I will note if that we were not operating from atmospheric pressure, which from our perspective is 0 because we're just going off of perturbation variables. If this was like, so you have P1 and then we had a P2 back here or some other tank, then you would be seeing those differences in pressure. P1 hat minus P2 or P2 minus P1, and same thing from here to there. All right, atmospheric pressure when we go to our perturbation variable simply becomes 0 because we're taking out all the static effects. And we could then, if we wanted, clear the Q and the R, bring stuff to the other side, and we actually have a homogeneous differential equation. And with that, I will leave you to our next problem. Bye for now.